everyone, and thank you for joining me here at ICCV 2025 in Hawaii. I'm Fengchen He from Huazhong University of Science and Technology. Today, I'm excited to present our work, titled Simulating Dual Pixel Images from Ray Tracing for Depth Estimation. Now, let's talk about the motivation. Dual pixel images are valuable for depth estimation, autofocus, and deblurring. But real DP depth paired data is hard to get due to varying DP disparities. Across cameras and settings, existing simulation methods from RGBD data lack realism. So we proposed STIRT using ray tracing to reduce the domain gap. Our contributions are fourfold. First, we propose a ray-traced DPPSF simulator to address the domain gap from lens aberrations and sensor phase splitting. Second, a pixelized DP image rendering module using an MLP narrows the gap between simulated and real DP images. Third, the DFDP model trained on STIRT generalizes better to real DP images for depth estimation. Finally, we collected the DP119 test set with diverse real-world DP depth pairs. Let's look at our method. Our pipeline for simulating dual pixel images from ray tracing includes three key parts: a ray-traced DPPSF simulator, a DPPSF prediction network, and a pixel-wise DP image rendering module. The process involves ray tracing on both the lens and the DP sensor to compute spatially varying DPPSFs, which are then used to render simulated DP images. This page focuses on the overview of ray tracing applied to the lens and dual pixel DP sensor. Specifically, Part A illustrates the process of ray tracing on the lens, while Part B shows the ray tracing on the DP sensor, which are key steps in our method to compute the necessary optical properties for simulating DP images. We evaluate real and simulated DPPSFs under f1.8 at 2 depths and 3 positions, as object point P moves from the optical axis. Real PSFL and PSFR show more phase asymmetry and aberrations. Existing simulators ignore these, creating a large gap, while our ray-traced simulator realistic results across all tested cases. We evaluated simulated versus real defocus left DP images at 0.5 meters and 2 meters. Other method simulations have issues like inconsistent pattern sizes, incomplete shapes, and texture shifts around the 1 meter focus distance. Ours produce the most realistic results. We evaluate DFDP models on for casual scenes. Other methods show partial relative positioning accuracy, but large absolute errors. Our depth estimation results demonstrate high accuracy in both relative and absolute positions. Here are more quantitative and qualitative results of depth estimation. The DFDP model trained with our STIRT achieves superior performance across most scenarios. And evaluation metrics. Simulated DP images help address scarce DP depth paired data that face a domain gap. Our STIRT framework uses ray tracing to calculate DPPSFs and render images, producing more realistic simulations. Models trained on STIRT generalize better to real DP images for depth estimation. Finally, we have attached the repository and website addresses of our project, as well as my contact information. Thank you all for your interest in STIRT and for watching. See you in Hawaii!